In this class, we have discussed about non-cytometric defect. In non-cytometric defect, we have discussed two types of metal access defect. That is, the first one is the metal access defect due to anionic vacancy. In that case, we have discussed when a sheet of sodium chloride is heated in the vapor of sodium, then sodium is deposited over the crystalline structures. In that case, the chlorine diffuses from the crystal lattice and react with the sodium deposited at the surface to liberate electrons. These liberated electrons diffuse into the anionic vacancy created by the chlorine and give its color that is known as absenter, due to which it develops color, and the color of sodium chloride is yellow in color. To the next, due to the same metal access defect due to anionic vacancy, in case of lithium chloride, what we have the color that pink, and the potassium chloride is violet in color. What we know, we have discussed that non-cytometric defect is of two types, that is metal access defect. The next is metal deficiency defect. We have discussed the metal access defect due to anionic vacancy, and to the next we will discuss the metal access defect due to presence of extra cation. In that case, we know the color of zinc oxide, it is white in color. Zinc oxide is white in color, but it turns to yellow on heating. Why it is so? Because of heating, the certain zinc oxide breaks and liberate oxygen, due to which an extra metal cation is there, which occupies the interstitial site, and hence in this defect we have an excess of metal cation. So we'll discuss it, that metal access defect due to presence of extra cation. What happens? Let us see. When we have the crystal of zinc oxide, when it is heated, then it forms Zn2 plus Zn2 plus oxygen half O2 plus 2 electrons. In this case, the color of zinc oxide, it is white in color. But due to this defect, it means if we have the crystal of Zn2 plus O2 minus Zn2 plus O2 minus Zn2 plus O2 minus Zn2 plus O2 minus Zn2 plus, here we have Zn2 plus O2 minus Zn2 plus O2 minus O2 minus Zn2 plus O2 minus Zn2 plus. This is the crystal. But when the crystal is heated, then the certain molecule, that is zinc oxide, we have this one, zinc oxide. When we heat it, then it is converted into zinc 2 plus and to the next one, 2 electrons. This zinc 2 plus, it means in the cytometric composition, if we assume that one zinc molecule is lost, then in that case, what we got, oxygen is liberated out. What is left? Zinc 2 plus 2 electrons. This zinc 2 plus, it occupies the interstitial site. For example, if we have the interstitial site, here, if it occupies Zn2 plus, then 2 electrons occupies the adjacent interstitial site. In this case, the electrical neutrality is maintained in this type of defect. The first point is that in this type of defect, we take an example of zinc oxide. When it is heated, then it forms Zn2 plus oxygen and 2 electrons. This Zn2 plus occupy the interstitial site, and 2 electrons occupy the adjacent interstitial site. Due to which the electrical neutrality is maintained. It means the next point is that electrical neutrality is maintained. The next, due to this defect, zinc oxide is white in color, but turns what? Yellow. When we see the cytometric ratio, it means 1 zinc is to 1 oxygen, 1 zinc to 1 oxygen. It means the cytometric ratio here is what? The cytometric ratio is what? The cytometric ratio is Z and O. It means it has the ratio of 1:1. But on hitting it, what is lost? Oxygen is lost. It means if oxygen is lost, in another way we can say that there is increase in the composition of zinc. That's why what we write on this defect, the composition becomes Zn what? 1 plus XO. X indicates the increase in the number of zinc cations. That means in this defect, due to breakdown of zinc oxide, oxygen is liberated, due to which lattice has an increased concentration of Zn2 plus. It means metal cation. Therefore, it is termed as increased concentration of Zn2 plus, and the new cytometric ratio, is Zn1 plus X O. To the next, we see in this type of defect there is increase in the number of metal cation. Therefore, it is known as metal excess defect due to presence of extra cation. Let us understand it once more. We will understand the metal excess defect due to presence of extra cation. It means when we have the crystal of zinc oxide, then when zinc oxide is heated, then it is converted into Zn2 plus oxygen plus 2 electron. This oxygen is liberated from the lattice. When this oxygen is liberated from the lattice, then what we have? We have Zn2 plus 2 electron. This zinc, but before that, before this defect, what we have the ratio? The ratio is Zn1 O1. Zn1 O1. It means they have the ratio of 1:1. But when we heat it, what we have? We have oxygen is liberated. When oxygen is liberated, then we have an excess of metal cation in the lattice, due to which we have an increased concentration. Therefore, the cytometric ratio becomes 1 zinc 1 plus X. X means the increase in the concentration of zinc metal cation. To the next, where this goes, this zinc 2 plus occupies the interstitial site, and this 2 electron occupies the adjacent interstitial site. Therefore, the electrical neutrality is maintained, but it is a type of non-cytometric defect. Why? Because the ratio is not maintained here. We know that the color of zinc oxide is white in color, but it turns to yellow due to this type of defect. We know that in this type of defect, the electrical neutrality is maintained. So the next we will discuss metal deficiency defect. There are certain compounds which are difficult to prepare in their cytometric ratio. For example, if we take an example of iron oxide, then it is difficult to prepare in cytometric ratio. Its ratio of iron varies from 0.93 to 0.96 to that of oxygen. In this case, there is deficiency of metal. Let us see how this occurs. Next, we will discuss the metal deficiency defect. Metal deficiency. Metal deficiency defect. Metal deficiency defect. In this case, if we take an example of preparation of compound of iron oxide, FeO, then in this case, the cytometric ratio of iron and oxygen is 1:1. But during the formation of lattice, what we got? We had the cytometric ratio of Fe. It ranges from 0.93 to 0.95 to O. It means it is not 1:1. It is 0.93 to 0.93. 0.93 to 0.96 is to O. This is 1:1. Why this is so? But we know in this case, what is the requirement of iron? The requirement of iron is 1, but it is lesser than 1. It means in this case, there is deficiency of metal. Let us discuss how this happens. During the formation of iron oxide, certain iron 2 plus are displaced by iron 3 plus. It means if iron 2 plus is displaced by iron 3 plus, then what is the ratio? It means if we want to displace 3 iron 2 plus, then it will be fulfilled by what one? 2Fe3 plus. It means 2 3 ja 6 power and 3 2 ja 6. It means if 2 iron 2 plus cations are, if 3 iron 2 plus cations are removed, then their vacancy can only be satisfied by 2 iron 3 plus cation. Due to this, here in this case, we have 3 iron which are displaced by 2 iron. Due to this, there is deficiency of metal. It is termed as metal deficiency defect. What we know? Certain compounds are difficult to prepare in their cytometric ratio. Certain compounds are difficult to prepare in their cytometric ratio. For example, during formation of iron oxide FeO, that is iron oxide, certain Fe2 plus, that is the iron 2 plus cation, certain iron 2 plus are displaced by Fe3 plus iron, due to which there is decrease in the concentration of iron in the lattice. What is that one? The next one. In FeO, the cytometric ratio of Fe and O is 1:1. That is Fe1O1. But due to this defect, the ratio, the cytometric ratio varies. Fe 0.93 to 0.960. Instead of 1:1, here it is 1. What is the concentration? This concentration is lesser than 1. Therefore, it is termed as metal deficiency defect. What we have discussed. To the next. What is metal deficiency defect? We know in case of iron oxide compound, the cytometric ratio of iron with oxygen is 1:1. But this compound is difficult to prepare in the ratio of 1:1. Why it is so? Because during the formation of this compound, what is the state of iron here? What is the state? It is Fe2 plus. This one is 2 minus. Then during the formation of this compound, certain Fe2 plus ions are displaced by Fe3 plus ion. It means what we have? It means in order to remove 3 Fe2 plus ion, only 2 Fe3 plus ions are enough. It means what we see the charge? 2 3 are 6. 2 3 are 6. It means 3 iron 2 plus can be displaced by 2 iron 3 plus, and the electrical neutrality is maintained. That means we remove 3 iron 2 plus by 2 iron 3 plus. It means there is deficiency of 1 iron atom. Due to this, there is decrease in the concentration of metal, and this is termed as metal deficiency defect. Clear? This is the type of non-cytometric, because the cytometric ratio is not maintained here. But what we see that in this type of defect, the electrical neutrality is maintained. To the next, we will discuss the electrical property of the solids. We know the solids have a wide range of electrical property, which varies from 10 to the power 20 ohm per meter to 10 to the power 7 ohm per meter. The solids are classified into 3 types based on their conductivity. They are classified as conductor, they are classified as semiconductor, and they are classified as the next one, insulator. Let us discuss them one by one. We know in case of conductor, it allows the electrical current to pass through them. To the next one, we know what is insulator. They have poor conductivity. And to the next, semiconductor, they have conductivity, and that ranges from a definite value, that is 10 to the power minus 6 to 10 to the power 4 ohm meter inverse. Let us discuss them one by one. The first one we'll discuss, that one is conductor. Their conductivity ranges from 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. To the next, insulators. They have lower conductivity, they have poor conductivity, which ranges from what 10 to the power minus 20 to 10 to the power minus 10 ohm inverse meter inverse. To the next one we will discuss, that is semiconductor.